and welcome to this module on cryptography. Let's see what we'll be covering in this video. We'll start off with what is cryptography, and then follow that with cryptography in the IT world. In other words, how do we use it? Then we'll look at the hashing algorithms, the symmetric algorithms, the asymmetric algorithms, and then finally we'll end off with a discussion on public key infrastructure. Let's get started. So what is cryptography? According to the definition, cryptography is the practice and study of hiding information. In other words, it's creating secrets. And in the IT world, it is the practice of changing plain text into ciphertext, and then vice versa. In other words, encrypting and decrypting. So that is what cryptography is all about. When you start studying cryptography, you will be overwhelmed with large number theory and algorithms and the history of cryptography, and you'll hear keys and blocks and ciphers and all these strange terms which will be very overwhelming to start with. But in your IT career, all you really need to do is understand where you use the different forms of cryptography, i.e. hashing, symmetric and asymmetric, which we'll discuss very shortly, and a little bit of theory on how the keys were created and how the different formulas and algorithms were created comes in handy, because there's a reason we've moved from 56-bit to 128-bit as an example. And to know the background really does come in handy. So let's go take a look at IT and cryptography. So cryptography in the IT world. Let's start with hashing. And you get two hashing algorithms, MD5 and SHA, but we use hashing purely for integrity checking, and I'll show you an example in the demo. But basically what we use the hashing algorithms for is to make sure that a file or data has not changed at all, and we use the hashing algorithms to verify that the file that you've received is exactly the same as the one you've sent, etc., etc. So you'll see when you download software from the internet, often the guys now provide you with the MD5 or the SHA algorithm, so that when you download the file, you can make sure that it hasn't been corrupted along the way and that it is the actual file that was put on the website. Then we get symmetric algorithms, and these are used also for integrity checking, because you would need the password to change the integrity of the data, but it also is used for confidentiality. In other words, making something a secret. So we take plain text, we apply a symmetric algorithm to it, which then encrypts it, and then the person receiving the file can decrypt it and read the message, so that if the file is intercepted between the sender and the receiver, the confidentiality is kept intact. And then the final one is asymmetric, which also has basis of integrity. It also has confidentiality, because it makes sure that the file is not changed. It also encrypts the file, but more importantly, it also provides authenticity. In other words, the person sending the file is really the person. And we see asymmetric algorithms in things like website certificates on HTTPS, so that you know when you go to google.com, you're actually going to google.com server. You're not going to a phishing site or a spoofing site that looks like google.com but isn't actually google.com. And those are the three basis algorithms and theories of where we use cryptography in the IT world. And it's important to understand that there are only three: hashing, symmetric and asymmetric, and where we use each one. So in your IT career, you generally stick with hashing for integrity, and you use asymmetric a lot for public key infrastructure, which we'll also discuss a little later. Symmetric algorithms are used literally just to encrypt data at a file or folder level, and you do use that sometimes, but generally in operational IT, you use hashing and asymmetric. So let's move on and look at the different hashing algorithms. So the first hashing algorithm is MD5. There are quite a few hashing algorithms out there, but the ones that you're going to find in your IT world is generally MD5, which is a 128-bit hashing algorithm. And then there's SHA. And SHA is pretty much the standard. It comes with SHA-1, which was 160-bit. Then SHA-2 came about, which came with 224, 256, 384, and 512 bits. And the new standard is SHA-3, which is currently in the process of being adopted. And all these character lengths or bit lengths pretty much just are the larger algorithms creating larger bit sizes. So the larger the algorithm, the more secure the hash is, so that you can prevent integrity from being tampered with. So the 128-bit was the standard, but as you can see, it's grown to 512 bits and beyond now to ensure integrity of algorithms. Let's move on now and look at the symmetric algorithms. The first one that you'll find, and the current standard, is AES. That has a block size of 128 and the key sizes of 128, 192, and 256. So what is a block size? The block size is simply the amount of bits or bytes that can be transformed by the block cipher. So in your PC world where you're trying to encrypt something, you can do it via a stream or a block. Now the block obviously is a lot quicker because you're taking chunks of data at a time. So the block size in AES in this example is 128, and the key size is the number of bits in key used by the cryptographic algorithm. The longer the key, the much more difficult it is to actually break the key. So as you can see, the newer algorithms will have longer keys and bigger block sizes. The older algorithms will have smaller block sizes and smaller key sizes. Let's move on. After AES, we get DS, which was the standard in the past, but as you can see, its block size is only 56, which is half of 128, and the key size was only 56 with an 8-bit of parity to ensure communication integrity. Then we got triple DES. Triple DES was moved up from 56 to 64 bits in block size, and the key size went to 168, 112, or 56. And then you get IDEA or IDEA, block size was 64 and key size 128. Cost had got two different costs. The one cost had a block size of 64 and a key size of 42, 128, so it gave you a variable key size length, which gave you a little bit of flexibility, so it could be from 42, 128, any number in between. And then the newer version of cost is a block size of 128 bits, and its key sizes are set at 128, 160, 192, 224, or 256. Then we get two fish, and two fish was block size of 128 and a key size of 128, 192, and 256. So as you can see, it's pretty much on par with the current standard, which is AES. Then we got blowfish, and blowfish had a block size of 64 and a key size from anywhere between 32 to 448. So even though its block size is a lot smaller, its key size up to 448 makes it a very, very strong encryption algorithm. Serpent was also set, it's one of the newer ones. Its block size is 128 and its key size is 128, 192, and 256. Pretty much the same as AES. And then there's Rindal, and Rindal is block size 128 and key size 128, 192, and 256. So what you'll notice is there's quite a few who have a block size of 128 and a key size of 128, 192, and 256. And this is because in pretty much a few years ago, NIST, which is an American standards organization, created what was called the AES contest. And it was pretty much to get rid of ciphers which had 64 bits or below because of something called the birthday paradox, and you can read up all about that online. And basically it says if there are 50%, you have a 50% chance of guessing the algorithm or start getting data leakage when you have more than 50% of the actual packets. So to prevent this, they launched a contest, and as you can see, the ones with 128 but block sizes and key sizes of 128, 192, 256, they were the ones that were entered. And Rendell is the standard that was chosen, has been altered slightly. So Rendell pretty much won the AES contest back in the day. And that pretty much talks about symmetric algorithms. As we discussed previously, use these to encrypt files, folders, hard drives, whatever the case may be, symmetrically. So there isn't an asymmetric key handshake. It's literally encrypting plain text into ciphertext using a key or password, which then encrypts the data. And the only way to decrypt it is to write is to enter that key or password so that the algorithm can reverse the encryption that it has done for you. Let's move on now and look at asymmetric algorithms. So now we move on to asymmetric algorithms. And an asymmetric algorithm is slightly different to symmetric because there are two keys. So there's a public key, which is known by everyone and which you can send to everyone. And there's a private key, which is only known by the owner. So the way it works is I want to send something to you, so I encrypt it with your public key, but only you can open it with your private key and vice versa. So Diffie-Hellman was the first asymmetric encryption algorithm, and it was invented in 1976. So it's been around for quite some time. And it set up this whole public key, private key exchange to enable encryption over distance. So in symmetric algorithms, there's only a private key. In asymmetric algorithms, there's a public key and a private key. And as I explained before, use the public key to encrypt it, and only the owner of the private key can decrypt it. That's pretty much how it works. Then after Diffie-Hellman came Al-Gabal, and Al-Gabal was based on Diffie-Hellman, and it was the predecessor to what came next, which was DSA, or the Digital Signature Algorithm, which is the United States federal government standard for FIPS and digital signatures. And there's a variation to DSA called the elliptic curve DSA, and it's a variant of that which operates on elliptic curve groups, which is a advanced mathematical concept that you can study further if you so wish. The other one that you'll find a lot out in the field, in probably the most, is RSA, and it stands for Rivest, Shamir, Alderman, which are the three scientists who invented it, and it's very commonly used for both encryption and for digital signatures, especially website certificates. And that's the end of the asymmetric algorithms. There's many more. There's also many more of the others. And you can read up about them. But this module, I'm just trying to touch on the ones you're going to encounter in the field. These are the most commonly used. And the ones that you need to understand are the ones that are the current standard and the ones that are most commonly used. Let's take a look at public key infrastructure. So, public key infrastructure uses the asymmetric algorithm. So it's very important for you as a security professional to know asymmetric algorithms and the whole basics around public key, private key. Why? Because we use it to create certificates, and the certificates you'll know about are the root certificate authorities and the normal certificate authorities. So you get certificate authorities on the internet, people like Thought, VeriSign, GoDaddy, Komodo, and they verify, and that's where asymmetric algorithms use authenticity, because they verify the authenticity of the site that you are visiting because of this whole public key, private key concept. So the certificate authority issues a certificate once they've authenticated you. They issue a certificate based on the public key, and then using your private key on your web server, you actually encrypt the traffic. That's how it works. So you get root certificate authorities, and those are certificates that are on certificate stores across all the different operating systems, Mac, Linux, Windows, whatever it may be, so that when your computer goes to a site, it already has the public key certificate on your computer, so it authenticates to the other public key just for confidentiality, and it encrypts the traffic for you. You also get certificate authorities on domains, and these aren't root certificate authorities, but they're used primarily in large enterprises to do authentication and encryption across systems and services on the local area network or within a local organization. The last thing we just want to chat about is X.509, and that is the standard for certificates. And it's very important to understand this concept if you're going to be a security professional, because the X509 standard pretty much covers the whole public key infrastructure, and those are the certificates that are issued. So understanding how certificates are issued, understanding how they use public keys, how you use a private key to make a private certificate, etc., is a pretty important concept, but you only really learn that by doing it. So I highly recommend you look at how to publish certificates and set up a certificate authority in a lab and take it from there. And that ends this module on cryptography and this theoretical video. Thank you very much for watching.